So a shuttle mechanism is one in which gets molecules from where they normally are to where you want to get them, but they can't normally cross the membrane. So let's think about this for a moment. Do we want NADH to be permeable to the mitochondrial membrane? Do we want NADH to be able to go in and out? No, because what would happen if NADH could come out? You wouldn't have electron transport. So we need to make sure that NADH stays in the mitochondria so that it can participate in the electron transport chain. Can you think of NADH that we've talked about a couple chapters ago that is not in the mitochondrial in the mitochondrion? The cytosol from what process? Glycolysis. We're not going to waste it. So what we need to do is get it into the matrix somehow so that it can participate in the electron transport chain. So that's what we're going to talk about. How do we get the cytosolic NADH, the NADH from our glycolysis, into the matrix so that it can contribute to into our electron transport chain? There's two. There's the Glycerol-Phosphate Shuttle, and there's the Malate-Aspartate Shuttle. And one is better than the other. One has a better, what I call, exchange rate. So the Glycerol-Phosphate Shuttle takes NADH from what we're making it in glycolysis. How many do you get from glycolysis for every molecule of glucose? Two, because you get one from each stage 2, right? So we get 2 of them. All right, so we get 2, and each one through this glycerol-phosphate shuttle will only make 1.5 ATP. All right, let's think about this for a second. What did I say about the PO ratio, or that exchange rate, when I put NADH into the electron transport chain? How many ATPs can we make? 2.5. So we're kind of getting not a good exchange rate here. This isn't such a good deal. What molecule only makes 1.5 ATPs? FADH2. Somebody's been studying. So FADH2 only makes 1.5. So what can you think happens to that NADH? Does it get transferred back to an NADH when we have an NADH in the cytosol? Do you think it gets transferred back to an NADH in the matrix? What do you think is going to happen? Maybe those electrons don't get transferred back to an NADH in the matrix. What do you think it's going to get transferred back to? FADH2. So you guys already know this. By me telling you that there was only an exchange rate of 1.5 ATPs, you knowing what the exchange rate for FADH2 is, and the real word is PO ratio, phosphorylation to oxidation ratio, but I call it exchange rate. What that exchange rate is for FADH2, you already know what's happening for the glycerol-phosphate shuttle. You take the NADH. You're going to give the electrons from the NADH. Remember, when I'm saying NADH, that's NAD with electrons. That H is a hydride. The hydride is the holder of the electrons. So you're going to give the electrons from the NADH to other molecules. When those other molecules that can pass through the membrane are going to pass off the electrons to something in the matrix, it's not going to pass it back to another NADH. It's going to pass it back to an FADH2. So let's see how that happens. You're not going to have to memorize this, okay? What I want you to remember is basically what I've already said, is that the electrons from the glycolysis NADH get passed through, all right, glycerol phosphate. That's why it's glycerol phosphate. So remember the name and the exchange rate. It gets transferred to glycerol phosphate, which can pass through the membrane. Then once it's in the matrix, it gets passed to FADH2. So all you have to remember for the glycerol-phosphate shuttle is the name, glycerol-phosphate shuttle, right? And that it starts out with the glycolysis, NADH. Those electrons get passed to the name, glycerol-phosphate. Glycerol-phosphate can make it through both membranes. And then once it's glycerol-phosphate's in the matrix, it passes it to FADH2. That's what I want you to remember. Sure. Let me answer Alex's question first.
Okay. Does it have to use FADH in order to get it off because it's harder to pull off?
It has to. In this case, it uses FADH2. I'm not sure why. Because remember I said, oh, you're going to see FADH2 when you're putting a double bond in. I'm not sure. I haven't investigated this. So it is sort of surprising that we're using an FADH2 for this, or an FAD to oxidize it back. It might be that it is harder to oxidize this one, but it might be just the way it is. Yeah, I'm not sure why. I don't have that answer. But that's good thinking. You were surprised that Alex was surprised that when we were oxidizing this OH to get back to our dihydroxyacetone phosphate, that what happened was we were oxidizing an OH, and usually we use NAD for that. But here we're using an FAD. So that was surprising because what I told you, when you see FAD as an oxidizing agent, you're going to see it putting in a double bond. Here, this is not the case. I'm not sure why it's using FADH2, or FAD is the oxidizing. All right, so again, one more time. What's happening is that we have the reverse of the reaction that happens in glycolysis. The one so what we're doing is we're taking NADH and we are oxidizing it to NAD. We're giving the electrons to glycerol-phosphate. Glycerol-phosphate is permeable to both the inner and outer mitochondrial membranes. Once inside the matrix, the glycerol-phosphate gives the electrons to FAD to make FADH2. The FADH2 enters the electron transport chain and only makes 1.5 ATPs. So when you're condensing your notes, the way you should condense it is saying glycerol-phosphate shuttle, underline glycerol-phosphate, say this is the molecule that gets across the membrane, and then NADH to FADH2. That's how I would condense it. The other shuttle is the Malate-Aspartate Shuttle. We don't have that as widespread as the Glycerol-Phosphate Shuttle, but it's found in kidney, liver, and heart, and it's much more efficient because the NADH is the electrons from NADH is transferred to another NADH in the matrix. It's a little bit more complex than the Glycerol-Phosphate Shuttle, but really what I want you to remember is that the malate is going to cross the membrane. So again, because we're transferring it from a cytosolic NADH to a mitochondrial NADH, we get an exchange rate of 2.5. So here, this is what's happening. Malate can get through. So the names are the molecule that it's going to get across the membrane. Here we're talking about both of them. So the malate is what's going to pick up the electrons from the NADH and cross the membrane. Here we're going to then, once we're in the matrix, we're going to pass it back to NADH. That's really what I want you to remember, that we're going to transfer the electrons to malate. Malate is permeable to the membrane, and then once the malate is in the matrix, it passes it back to NADH. But I want to talk about it a little bit more. In glycolysis, one of the reactions that produces NADH, or the reaction that produces NADH is, or the last one, I'm sorry, is going from malate to oxaloacetate, right? That oxidation. So we're reducing NAD to NADH. So we're running that reaction in reverse here, going from oxaloacetate to malate. So that's a reduction. So we're oxidizing the NADH. So this is the reaction from glycolysis, running it in reverse. Citric acid cycle that is running in reverse. But it's happening in the cytosol. So we have a different a cytosolic enzyme. So we're running it in reverse. We let the malate cross the membrane. The malate then runs it in the forward direction to have the oxidation, and so we're reducing the NAD. We then take the oxaloacetate and we transfer a group, and we make aspartate that can go back out. I don't really need you guys to remember that part. It's part of the name, so that's why I need you to remember it. But really, malate crosses the membrane, NADH to NADH. Fair enough? Any questions? Are you awake? Yeah? It's too sunny out not to be awake, right? Okay. I'd like to complete our story of our metabolism from glucose. So we're done now talking about metabolism of glucose. So we're going to do sort of an accounting. And what we have here, this is right from your textbook, is the different things that are going on. So here we have glycolysis, and these are the different reactions that either use up ATP or produce NADH or FADH or NADH here. And here, this is the pre-citric acid cycle. This is the citric acid cycle. And then this is the exchanging of everything that we've made. Now, we have sort of a two accounting here. The reason why we have two accountings here is based on the shuttle. So what I'm going to do is sort of focus on the glycerol-phosphate shuttle first, and then talk about things later. So let's focus on glycolysis here, this top one. This is ATPs. We use up an ATP. So just put your hand over this one right now. We're not going to pay attention to this. So this is sort of like, let's focus just on this. This is if we use the Malate-Aspartate Shuttle. So if we phosphorylate glucose, we're going to use up an ATP, so -1. We phosphorylate again to fructose 6-phosphate to fructose 1,6 bisphosphate. So now we're in the hole too. We're paid our college tuition. Now let's make some money, right? Here we make an ATP. All right, that's one step. But remember, this is stage 2, so this happens in duplicate. So we're going to make 2. Now we're even. You paid off your student loans. And then, happens pretty quickly. You went to community college like us, so you pay off the student loans quickly. And then, remember, we make, when we take PEP and make pyruvate, we make our net 2. Then we also have the NADH that we make when we oxidize the glyceraldehyde 3-phosphate. So here, the NADH, we get 2 of those as well because it's happening in duplicate. So here we're exchanging that. The pre-citric acid cycle, because remember it's happening in duplicate, we're putting 2 pyruvates through. So we get 2 NADHs, because each time we put a pyruvate through the pre-citric acid cycle, we get 1 NADH. So here is our net of 2. Now let's talk about the citric acid cycle. We get 2 molecules of GTP. We're going to count that as 2 ATPs, because that phosphate can be just transferred to ATP. So we're going to net 2. And then we get, because we oxidize isocitrate and alpha-glutarate and malate, we get 3 NADHs from our citric acid cycle. But remember, this is happening in duplicate because we started out with 2 molecules of pyruvate, so everything is happening in duplicate. So we get a net for every molecule of glucose that we started with, we get 6 NADHs. We get 1 FADH2 for every citric acid cycle. So again, in duplicate, we get plus 2. So here, what we've started with is we have a net, a negative 2, or not a net, we're negative 2, we add 2, NADH, NADHs, more ATPs, and more NADH. So now what we're going to talk about is taking these NADHs and these FADH2s and exchanging them into our electron transport to make ATPs. So these 2 NADHs we just talked about, they're in the cytosol. So they have to go through our shuttles. If we use the Glycerol-Phosphate Shuttle, the 2 NADHs will make how many ATPs? 3, right? It's right here. Because each one is 1.5. 1.5 times 2 is 3. Now, if we use the Malate-Aspartate Shuttle, 2 NADHs will make 5. So that's where the 2 lines come from, guys. So that's 5. All right. Now, this is in the mitochondria, so the 2 NADHs will make 5 ATPs, because 2.5 times 2 is 5. And then we're talking about the FADH2. 2 FADH2s will make 3. The 6 NADHs, 6 times 2.5 is 15. So if we use the Glycerol-Phosphate Shuttle, we have 2 fewer ATPs than if we use the Malate-Aspartate Shuttle. So depending on what shuttle you use, you're going to net for every molecule of glucose either 30 or 32 ATPs. That's a lot. From here down, you need oxygen. So all of this down here, all these goodies that we made here are from having oxygen. The ATPs, if you're anaerobic, are only from the 2 that we get up here. So that's quite a difference. Having oxygen around definitely makes it more efficient use of your energy. Any questions? I'm not going to ask you to do an accounting. I would ask you specific questions about this. How many do you get from glycolysis? How many, what is the ratio of turning an NADH in? What is the difference in using the different shuttles? So that, I'm not going to have you do this accounting again. That was a lot. Okay?